we're on right now. You try to whatever you're gonna share. Oops. There.
Sorry, just a second. I think this should
Yeah,
work.
your time.
Are you seeing my slideshow? Or
I can see the Windows log. Que vi una cosa así. ¿Qué es eso? Pantalla lo veo.
Oh, here we go.
Okay. Perfect. We can see this.
Okay.
So just action. This is the one topology 7 9th to this is session for this. This is we're finished fall last year. You invited to Nipissing University. And well, I don't know if I pronounced it correctly. Could you? So feel free to.
Right. You can see me and hear me fine?
We can see your slides.
All right. Okay, I'll just get started. Thank you for having me. All right. So I'm going to be talking about accessibility of points of arc-like continua. This is work I did with Anna Anusic and Logan Hain in the past few years. Right, so the question we answer is known as the Nadler-Quinn problem. It was posed by Nadler and Quinn in 1972. It asks if you have any arc-like continuum X and a point in X, if you can find a plane embedding of this continuum with that point accessible. So for some quick review, by a continuum, we mean a non-empty, compact, connected metric space. And if we have a continuum, we say it can be embedded in the plane if there exists some homeomorphic continuum, which is a subspace of the plane. It is known that every arc-like continuum can be embedded in the plane. If you have a plane continuum, we say a point is accessible if there exists an arc, which is in the plane, which only intersects the continuum at that point. By an arc, we just mean a space which is homeomorphic to the unit interval. A continuum is arc-like if it can be expressed as an inverse limit on arcs. So here I have included a picture of an inverse limit on arcs. We always take our factor spaces to be the closed interval -1, 1, which we denote with the I here. Each of these are called factor spaces. Each of our these sets -1 to 1, and each of these maps Fn are called bonding maps. All right. So as a quick example, the double sine 1/x continuum is an arc-like continuum. We have these two rays. If we look at this, embedding of it in the plane here, we have two rays which compactify on an arc in the middle. And with this particular embedding, any point on this arc, which is not an endpoint, is in this embedding not accessible. We cannot draw an arc that will only intersect the continuum at this red point here. On the other hand, if we take this left ray and tuck it over top of the right one, then we have this entire arc exposed on the side, and so we can make any of these points accessible by drawing an array, an arc. All right, so if we consider some arc-like continuum X, which is the inverse limit with bonding maps Gn, and we have a point in X with coordinates x1, x2, x3, and so forth, if infinitely many of these coordinates are equal to plus or minus 1, then the point X is an endpoint of our continuum, and we know that we can embed our continuum in the plane with any endpoint accessible. So for that reason, we will assume that that each of our coordinates are not equal to plus or minus 1 for all n, and if we do this, then we can find a homeomorphism to an inverse limit for which all bonding maps map 0 to 0, and this point X gets mapped to the point 0, 0, 0. So we can narrow down our question then to this formulation here at the bottom, where we assume our continuum is an inverse limit with bonding maps which all map 0 to 0, and then we want to find a plane embedding for which the point 0, 0, 0 is accessible. So in 2018, Anna and some others proved that if for each of your bonding maps, you have that the point 0, 0 is not in a zigzag, as they called it, then you can embed the continuum in the plane with the point 0, 0, 0 accessible. So that is the standpoint from which we attack this question. So what we do is we break down this zigzag, as they called it. So we define what are called positive and negative radial departures. So a radial departure is a pair of points, x1 and x2, x1 less than 0, x2 greater than 0, such that the range on the open interval x1, x2 is equal to f of x, the open interval f of x1, f of x2. If it is a positive radial departure, which is here in blue. So if I have this point x1 and this point x2, we can see that nowhere in between x1 and x2 do we strike these dotted lines here. So in blue, we have indicated a positive radial departure, and in red, we have indicated a negative radial departure. So with that breakdown of the zigzag, we then reformulate their theorem, and we say that if we can find, if each of our bonding maps have only radial departures of the same orientation, so either all positive or all negative, then we know that we can embed it. We can embed the continuum in the plane with the point 0, 0 accessible. If we have both positive and negative radial departures present, then the point is in a zigzag, and we don't want that. All right. So to make use of this result, our goal is to find, given some inverse limit, we want to find a homeomorphic inverse limit for which all bonding maps have only radial departures of one orientation. In our study, we always want them to be positive, so we want no negative radial departures. So before I discuss that more, I will review some ways in which we can have homeomorphic inverse limits. So first, if you drop finitely many coordinates, you have homeomorphism. So that is to say, the inverse limit with bonding maps f1, f2, f3, f4, and so forth is homeomorphic to the inverse limit with bonding maps f2, f3, f4, so forth. So we can drop finitely many of these coordinates and still have the same space. Also, if we have an inverse limit where each of the bonding maps, let's say Gn, are compositions of these bonding maps Fn in our original inverse limit, then we have homeomorphism. Then we have a homeomorphism between these two inverse limits. And then this diagram here it gives us, it shows a way in which we can have a homeomorphism between the inverse limits, the inverse limit with bonding maps Fn and the inverse limit with bonding maps Gn. It just derives from these first two that I already discussed, but it's the one that we will focus on, so I included the diagram. Yeah, it tells us that if we have for each of our bonding maps, we can find a factorization. So let's say F1 equals T1 ring S1, F2 equals T2 ring S2, and so forth. Then we are going to have that the bonding maps, the inverse limit with bonding maps F1 and the inverse limit with bonding maps G1 are homeomorphic if each of these Gns equals Sn ring Tn plus 1. Finally, I won't go into this one too much, or really at all. I'm not going to go into it at all, but it will be used, so I'll just touch on it. If we have inverse limits with bonding maps Fn and Gn, and for each n, these bonding maps Fn and Gn are sufficiently close according to criteria defined by Mu-Dushevsky, then we have a homeomorphism. Yeah, I won't go into the criteria, but it just means they are approximately, these bonding maps are approximately the same. Then we have homeomorphism. Okay, so with that, the general approach, I just grabbed the more interesting commutative diagram. Our goal is to, given our inverse limit x, our goal is to find a factorization of each bonding map so that the maps S1 ring T2 and S2 ring T3 and S3 ring T4 and so forth all have no negative radial departures. So if we can make it so that each of these compositions of maps only has positive radial departures, then by that theorem from earlier, it would follow that we can embed X in the plane with 0, 0 accessible. A tool we have in doing this is the following proposition. It tells us essentially, so if we have a map T and a map S, and X2, X3 is a negative radial departure of T, where X2 and X3 are mapped to Y2 and Y3, and Y2 and Y3 are a positive radial departure of S, then when we take the composition S ring T, we will get that X2, X3 is a negative radial departure of S ring T. Similarly, if we look at X1 and X4 here, if X1, X4 is a positive radial departure of T, Y1, Y4 are their images, and Y1, Y4 are part of a negative radial departure of S, then again, we will have a negative radial departure of S ring T. And then, yeah. The terminology I will often use for this is I will say we have a negative departure of T landing on a positive departure of S. So whenever we have a negative departure landing on a positive departure, then in our composition, we get a negative departure. Similarly, if we have a positive departure which lands on a negative departure, we have a negative radial departure. And if we have a positive radial departure landing on a positive radial departure, we get a positive radial departure in our composition. Yeah, the last one, which I didn't include a drawing for, is if we have a negative radial departure lands on a negative radial departure, then you also get a positive radial departure in your composition. All right, so with that in mind, we developed a method for factorizing maps, which is going to be very useful for us, and in general is just an interesting concept. So yeah, this factorization, we call it a radial contour factorization. I will give it in a moment, but first I need to give some terminology. So we define a couple things here. First, if we just look on the right side, so to any point right of the point 0, 0, a right departure is a number greater than 0, which is breaking new ground, so to speak. So if you have a point x1, which is smaller than x, f of x1 does not equal f of x. So if we look at this map in orange on the right, I indicated with orange right departures, and then again with red some right departures, and then some right departures here as well. Left departures are defined symmetrically, except now we go to the left from 0, so we have departures here, here, and here. All right, we say a departure is positively oriented if it's above 0. So in orange, we have all of our positive departures. And we say it is negatively oriented if it is below 0. So here in the red, we have indicated our negative departures. And last, we define contour points. So if I just look on the right first, and it'll be defined symmetrically for the left. A contour point is any departure for which the departures soon after have opposite orientation. So if we look at alpha 1 is the last positively oriented departure before we see negative departures. Similarly, we have alpha 2 is our last negative departure before we see positive departures again. Yeah. So with that, we can go on to define our radial contour factorization. I don't define it formally, but I'll just sort of visually indicate how we find this factorization. So given some map, what we do is we take our contour points. We take our contour points on the right, and we evenly distribute them across the interval 0, 1. So on the right here, and then we basically just define it to be linear in between. So we have 0, 0 stays at 0, 0. This alpha 1 went here, alpha 2 went here, alpha 3 went to 1, and then we defined it to be linear between. Symmetrically, we do this on the left, like so. And essentially what you get is your initial map, but without all of the extra noise and zigzagging. So we call this map here our radial contour factor, and we denote it by TF. So that this becomes very important. And then our radial meandering factor is just a map S for which this equality holds. So F equals TF ring S. It's not going to be unique, but you can always find at least one which is sign preserving, which is good. Yeah. So Using radial contour factorizations, we were able to prove this theorem here, which is that if you have three maps, F1, F2, and F3, which all map 0 to 0, and we have that the radial contour factor of F1 equals the radial contour factor of F1 ring F2, and similarly, the radial contour factor of F2 equals the radial contour factor of F2 ring F3, then we can find a map S such that, the composition TF1 ring S is going to be equal to F1 ring F2. What is good, S ring TF3 has no negative radial departures. So I'll just give a super quick summary of how we do this. Essentially what we do is I have some images here of maps F1, F2, and F3. For simplicity, they are all equal to their radial contour factors, so we don't have any unnecessary noise. They're all to the point we have all the distinguishing features present and nothing extra.
It's very unrelated to the course. Are you familiar with
all right, so these maps, which are equal to their radial contour factors, if we consider F1, we have that if we take the radial contour factorization of F1, which gives us this S1 here, and we consider, for us in this particular situation, S1 is going to be the identity because F1 equals TF1. But we take S1 ring F2, and essentially what we do is we look at F3, and any place where we have a negative radial departure landing on a positive radial departure. Oh, we don't have that here. But any place where we have a negative radial departure of TF3 landing on a positive radial departure of S1 ring F2, we can essentially like bridge between our contour points of S1 ring F2, either in our first quadrant or in our second quadrant. And that will help kill whatever positive or negative departure is the problem. So in this picture, I think we have, what do we have? Yes, we have a positive radial departure here in F1 at B1 and B8. So we have a positive radial departure of TF3 landing on this negative departure of B1, 7. And so to prevent a negative radial departure in the composition, we bridge across these contour points. And in that way, we eliminated the negative radial departure. So whenever we do this, we don't lose the equality. This S is chosen in such a way that we still have it so that TF1 ring S equals F1 ring F2. All right. So this is good. And to use our theorem on an infinite sequence of maps, what we want is this property to hold for all n. So if you have an inverse limit with bonding maps Fn, as indicated here, we want that for every n, the radial contour factor of Fn equals the radial contour factor of Fn ring Fn plus 1. Right. So in that sense, we want our inverse limit to we want the radial contour factors to stabilize in this sense, because if we can do that, then we can factor these compositions as we did in the previous step, in the previous slide. So we can factor each composition F1 ring F2 with TF1, and then that that map which has no negative radial departures. Sorry. If we take F1 ring F2, we find TF1 and S12 such that TF1 ring S12 equals F1 ring F2, and S12 ring TF3 has no negative radial departures. So if each of these compositions, S12 ring TF3, S34 ring TF5, and so forth, if all of them have no negative radial departures, then these GNs have no negative radial departures, and then we can embed the continuum in the plane with 0, 0 accessible. So to achieve this stabilization, what we do is, given a map, we truncate it with respect to some finite set V. So if we have some bonding map F given here, we can choose some finite set which contains -1 and 0. Here we have it indicated where the dotted lines are. We truncate with respect to this set, so we take off all of these jagged tips that stick out, and we flatten them. And in doing this, whenever we consider our truncation now, we know that our truncation, the radial contour factor, is only going to have contour points mapped into V. So all of our contour points are going to be mapped into our finite set V. And we have a pretty close approximation still of our initial map. So that is the approach we take. And yeah, I think that's all we need to get started in my overview of our proof of the theorem. So we answered the Nadler-Quinn problem in the positive. So that is, we stated that for any arc-like continuum and any point in that continuum, we can embed the continuum in the plane with that point accessible. And yeah, all of the concepts discussed earlier are used in this proof, which I will overview now. So we take some continuum X, which is the inverse limit with bonding maps Fn. And what we do essentially is we consider all compositions of these bonding maps which end at our first factor space. So the last function we apply is the function f1. We consider all compositions, and given some finite set v1, if we truncate each of these compositions with respect to v1, then because v1 was a finite set, there are finitely many options for where our contour points can be mapped. And so by pigeonhole principle, infinitely many of these must have the same radial contour factor when truncated with respect to v1. So we'll call this radial contour factor T1. After that, what we do is whichever compositions I had indicated in red in the previous step, all of those compositions we consider again, but this time instead of including whatever capital F1 was, they end at wherever F1 begins. Of all of these compositions, we do the same thing. We choose our set, this time our set V2. We choose it to be equal to F1 inverse of V1. And now again, if we truncate all of these compositions with respect to V2, we will get that infinitely many have to have the same radial contour factor because, again, the set V2 is finite. Right. We more or less continue on in this way. There are like some technicalities that would have to be addressed if I were to keep going on with this process. But we more or less continue on in this way. All right. So through this recursive process, we obtain maps Fk, which are all compositions of our initial bonding maps. And we obtain our finite subsets V1, V2, V3, and V3 primed, V5 primed, V7 primed, etc. These are all subsets of -1, 1, such that for every odd k, Vk plus 1 is going to be equal to the inverse of Fk Vk. And Vk plus 2 contains Vk plus 2 primed, which is going to be equal to Fk plus 1 inverse of Vk plus 1. And by our choice of F2, because we chose it from the red arrows in the step before our selection of F2, we know that F1 truncated with respect to V1 has the same radial contour factor as F2. F1 ring F2 truncated with respect to V1. Now, we have our lemma, a lemma which tells us that if you have any maps F and G and a finite set V, if F inverse of V is finite, then we're going to get that F truncated with respect to V, ring G truncated with respect to F inverse V. We're going to get that equals the truncation of F ring G with respect to V. So since we chose our VKs in that sense, where V2 has to equal F1 inverse of V1, that means that for every odd k, so here with 1, we have F1 truncated with respect to V1, ring F2 truncated with respect to V2, equals F1 ring F2 truncated with respect to V1. And then from, as I just mentioned previously, we know that the radial contour factor of F1 ring F2 truncated with respect to V1 equals the radial contour factor of F1 truncated with respect to V1. So now we have that, that stabilization that we wanted to see earlier. Yeah. So we apply the theorem so for every odd k, we can apply this theorem now, where if I just talk in terms of F1 and F2, but the same can be said for any odd k. If we consider F1 truncated with respect to V1 as our F1, and F2 truncated with respect to V2 as our F2, and then some other map, which I won't give you, as our F3, we have the property, we have this stabilization property that we wanted. And so we can find maps T1 and S12, which are equal to F1 truncated with respect to V1 ring F2 truncated with respect to V2. And then we can also get that here, S12 ring T3 truncated with respect to V3 primed, V3 primed, is going to have no negative radial departures. And then the same will hold for all odd k greater than 1 as well. So we do this for all odd k, and we get this diagram. We can make sure we chose each of our VKs fine enough so that the truncations are close enough approximations so that the inverse limits described by this first row and second row are homeomorphic, and also so that the inverse limit described here and the inverse limit described here are homeomorphic. And then in the middle, this row 2 and row 3, these inverse limits, these diagrams commute. So these two inverse limits are homeomorphic. And so each of these inverse limits is homeomorphic. So with that, we stop. So we have that X is homeomorphic to the inverse limit with bonding maps S12 ring T3 truncated with respect to V3 primed, ring S34, bonding maps, which are these compositions here, S12 ring T3 truncated with respect to V3 primes. Next bonding map is S34 ring T5 truncated with respect to V5 primed. And each of these compositions has no negative radial departures by our construction. And so we have that our continuum X is homeomorphic to an inverse limit in which all bonding maps have only positive radial departures. And so we can conclude that for any arc-like continuum and point in that continuum, there is an embedding of the continuum with that point accessible. All right. I went super fast, I guess, but here are some quick corollaries I can also mention. The first is a generalization of the Nadler-Quinn problem. So it tells us that if you have a continuum, which is the union of an arc-like continuum and a ray, which is disjoint from your arc-like continuum, where the ray compactifies on some subcontinuum of your arc-like continuum, then we can embed that space, that continuum in the plane. So the Nadler-Quinn problem was our positive results gave a positive answer to this, this corollary for the case when our subset of the arc-like continuum is just a single point. We also have that this corollary, which was sort of the incentive for Nadler to ask the Nadler-Quinn problem in the first place. He was wondering if any compactification of a line with an arc-like continuum remainder could be embedded in the plane. And since our answer to the Nadler-Quinn problem is yes, it can be somewhat quickly proven that this can also be answered in the positive. So any compactification of a line with an arc-like continuum remainder can be embedded in the plane. Here are just two examples. They're both variants of the Warsaw circle. Yeah, in one case you have a circle-like continuum, in the other a noose-like continuum. But yeah, they can be embedded in the plane quite clearly. And yeah, that is all I have. So thank you. I'm sorry I went so fast.
Thank you very much. Let's Andrea with. Well, thank you very much. Well, first, before I start asking questions, I'd like to know if you can hear it. Okay, is this says it's fine?
It's sometimes fine.
Sometimes, okay. Sometimes it has problems. Understand the question? To repeat it. Yeah, very well. That I'm the only professor here to ask questions. Of course, I would your paper very understand all the details. Yeah, it makes sense. So, for example, first truncation, and that you're doing it to first you want a simpler version of the problem. Well, you that says that if you have inverse limits and close, the limits are, well, perfect.
You're asking about like when inverse limits are homeomorphic if they're close enough.
I remember there was at the big. Well, you didn't that F and G Mudishevsky's, right?
Mm-hmm.
I understand that you're using the functions and you're using that.
Yeah. So if we choose our finite set to be fine enough, we can get that these truncations are close enough to the initial whatever your starting point was for every bonding map. Yeah, I didn't go into like how close they have to be, but we can get them. We can always get them close enough.
Yeah.
So that the criteria is met.
Okay. So I got that part. That's why you're truncating. And the other part that's probably harder, well, is these if you're defining a function t subscript f. Could you try to explain it again? What those functions do in short, if possible?
Which function? Sorry.
I don't know how, I don't remember how you call them, but for each function f, you defined t subscript f.
Yes. Sorry.
I don't remember.
Yeah, the radial contour factors. I probably should have dwelled on those longer.
Radial contour factors.
Yes. So this is what you're asking about?
I'd like to understand better. Oh, you already said. I would like. Could you? I don't know. Doing. What's the relation between f and?
Explain like the correspondence again.
Yeah. Well, yeah. How do you define?
Okay. Yeah, I can try to do better. So basically, these departures, which I defined earlier, they're basically any points heading away from the point 0, 0 towards either -1 or 1. They are points where your map is visiting some value for the first time. So here in orange, we as we go to the right, we are visiting values, y values for the first time. Then we start revisiting values. So I left that black. So all of these orange points are departures because we're just breaking new ground. Our map is breaking new ground, but then it does some revisiting until it gets to the red and it starts like seeing y values for the first time. So we're breaking new ground in this direction. Then we go up and down and we just revisit values we've already seen before we start to see new values again. And then everything after that, since we've now seen all possible y values, so all values in between -1 and 1, we don't bother with any of this because it's just additional noise. So what this radial contour factor does is it preserves all of these radial departures. It preserves their occurrence and the order in which they occur. So here we have like at the same y value. So we first, as we go to the right, we go up to say I think that's 1/3. Maybe it's 1/3. I don't know. We go up to 1/3.
It's 1/3.
Before we go down again. So our radial contour factor goes up to 1/3 and then it turns back around. Then after that, we go down to -1 and we have all of these departures. So we do the same thing over here. We go down to -1. Then we have some noise where we do a little bit of zigzagging, but we're not visiting any new values. So we don't worry about that. We want to just try and like flatten out all of the noise. So we just draw an arc to the end. And at this point, we have
Okay.
seen all values in our range. So we are done, essentially. The radial contour factor, the idea with it is it preserves the general, maybe not shape, that's not a good word, but it preserves all of these departures, all these first occurrences of y values in your range. And then it just flattens out any of the noise, which doesn't do anything to give us positive or negative radial departures. And since our concern is about positive and negative radial departures, we don't worry about that noise so much. And then I think, yeah,
that's just keeping the of when right the first time I didn't cross, but thank you very much. So let me well, first the online participant questions to ask. Unmute yourselves. Probably nobody's asking anything. Okay, so let me, in the meantime, let me ask the students if they have questions. Let me ask. I'm going to speak Spanish for a while. ¿Alguien tiene alguna pregunta? Si quieren, y lo en inglés. Fíen decirlo. They don't want to ask a question. They said. Much. Well, it's nice. By the way, but maybe you didn't hear. Well, yeah, he's not here anymore. Anyway, talk, Andrea. One thing I said is I don't saying your correctly, please. How it's pronounced?
Are you asking how my name is pronounced?
Yeah, we know how it. Speak native English. How it's.
My name's Andrea Ammerlaan. I hope that's what you're asking.
Andrea, perfect.
Ammerlaan.
It's because pronunciation it's other. Thank you very much.
Thank you.
Finish the goodbye coming.